All right, today we have Dexter Chua, who will be telling us about the secondary steamer algebra.
Okay, so I guess here we're here to do computations, and the thing that I personally like to compute the most is the Adams spectral sequence, or the homotopy groups of spheres. I mean, we use the Adams spectral sequence to compute the homotopy groups of spheres. And so I'll start by talking about the Adams spectral sequence. The starting point of the Adams spectral sequence is the steamer algebra. So I assume most of you are familiar with the steamer algebra, but I'll just write things out to set the stage for what's going to happen next. So the steamer algebra is the algebra of all co-homology operations. So you can define as A, this sum over all k, pi minus k of the endomorphism object of Fp, and this endomorphisms over spectra, if you want to be explicit. And then the cohomology of a space is sum over all k, pi minus k of maps from X to Fp. So this is a very standard definition, the steamer algebra X on the cohomology of a space, and this gives us this Adams spectral sequence, which goes from X over A of the cohomology of X to Fp, it converges to the P completed homotopy groups of X. So this is all familiar, and a very important thing about Adams spectral sequence is that even though the E2 page is a bit of a mess, there are lots of things going on. We don't have a good, full description of the whole thing. We can calculate this with a computer. Can be computed with a computer. And the computer doesn't just tell us what this is as a group. If it just does that, it will be pretty useless. What it actually gives us is it gives us the product structure. So there's a product structure. And the Leibniz rule. And combining these, we can use it to compute lots of differentials. And this is, I mean, if you don't have the product structure, it's just very hard to actually do calculations. You would just have to resolve each pi degree individually without reference to other pi degrees, and that's just very hard. So the product structure sort of is the first step in being able to compute anything, but it's sort of so ingrained that we don't think that much about it. But it's there, and then if you're sort of done with the product structure, you've exhausted all the products you can try. You can try messy products, which the computer can also calculate, and so on. So the point is that a lot of these things, the starting point is a lot of it can be done by computers, and then humans sort of sit down and try very hard to sort of compute the differentials. So the topic of today is sort of another way to get lots of differentials from a computer, and that sort of involves the secondary steamer algebra instead of the ordinary steamer algebra. And the idea of the secondary steamer algebra is to not only capture cohomology operations, but secondary cohomology operations and sort of the action on the cohomology groups. So if you want to define or work with secondary cohomology operations, what we need is not just a list of all cohomology operations, but we also need to understand homotopies between cohomology operations. So this sort of suggests the following definition. So we'll call this B. This is, we also take the sum of all k, but now instead of just taking homotopy groups, we sort of take two layers in the Postnikov tower together, and we need to do a shift, and then end of Fp, and then we can define the secondary cohomology of a space to be sum over all k, basically the same thing. Suspension k maps from X to Fp. So this is a secondary steamer algebra and the secondary cohomology. And we'll later see that this somehow encodes all the information you need to compute all secondary cohomology operations acting on the cohomology of a space. So before I say a bit more about this, I just want to make a quick observation, which is that on homotopy groups, these are not very interesting. So the homotopy group of the secondary steamer algebra, well, if you just look at this, you basically have two copies of the ordinary C-knot algebra. So this A adjoint tau, mod tau squared, where tau is in pi1 of the suspension of n of fp. So it's sort of the identity, but in like the other piece, the funny bit of it. And then the homotopy groups of the secondary cohomology, this is the ordinary cohomology adjoint tau mod tau squared, and this as a pi star b module. So as some of the homotopy groups are not interesting, what's interesting is the connecting bits between the different things. So this sort of a remark that will be a bit important later on. Okay, so what can you do about this? So the first thing about the C-knot algebra that makes it actually usable is that we know what it is as a ring. We have generators given by the C-knot squares, and then we have relations given by the Adam relations, and this sort of presents the whole thing as a ring. So the first thing, so this was studied by Bowers in like the early 2000s, and he did a lot of amazing work on it. So the first thing he showed was the following. So if we just look at the definition, it a priori is sort of an E1 ring over spectra, and not something that's nice, but Bowers showed that this is a DGA over Z mod P squared. So this is sort of a very important result. It means that we can actually do homological algebra over the secondary C-knot algebra. If we just have some general spectral ring, then it's very hard to concretely work with it. And Bowers not only showed that it is a DGA, it sort of described this explicitly as a DGA in terms of like generators and relations. Explicit computation. And the reason we care about this at all is the following result, which is by Bowers and Giblads. I'm not sure if I'm pronouncing this correctly. So knowledge of B and the secondary cohomology of X gives an algorithm to compute all Adams D2 differentials of X. So this is sort of a remarkable result. Previously, we had an algorithm that computes the E2 page that's sort of known for a very long time, and we use this algorithm as the basis of like most things we do with the spectral sequence. And now they say there's this algorithm that just computes all D2s. And if you're wondering why hasn't D2 been like a solved problems since the 2000s, the answer is that they did implement this algorithm, but they only ran it up to t equals 40. And all of those differentials were known. So they didn't, I mean, it wasn't like groundbreaking news because they just computed known stuff. It just gets slower and slower as you progress, and it just didn't produce things that are new. And I think people who do calculations did not think too much about this. There was still quite some work from a theoretical point of view trying to understand this a bit more, but it just wasn't that prominent in sort of like the more computational side of the world. So I think around a year ago, I saw this, and then I just thought about it, and I was like, can I implement this again? Like, I mean, we have faster computers, maybe we can go further, and there are also some other simplifications that we can make. And then I looked at it, I implemented it, it worked, and I did a few more extensions, and I got some quite useful results out of this. So most of what I did is sort of built on top of what Bowers did. But so my proofs, most of my proofs are independent of what Bowers did. So if you don't want to read work from the 2000s, you're free not to. You can. My thing is mostly independent, except that I did not reproduce the computation of the secondary C-knot algebra. So that part is hard. I don't know how to do it. Bowers did it, and I'm happy to just use his computation. But the rest of the theory is reproduced in what I did. So these are the results. The plan is that this will be on the archive in a month or so. I've been saying that since November, so let's see how this goes. So some of this is already on the archive. So this one is. So the first thing I did was I just computed lots of D2s. So compute all D2 differentials up to the 140th stem. So I should say that most of these differentials are not hard. I mean, a lot of them are new because no one's bothered to look that far. But some of them are hard, but most of them are not hard. It does produce something new that we previously didn't know. For example, there are a few D2s in more stable stems that were previously unknown. This algorithm just tells you what they are. So we compute all D2 differentials up to 140th stems. That's pretty useful. We sort of extend the algorithm to general X. So I'll say something about this. So previously, like Bowers already described how to do this for a general X. So what remains is to figure out what is the secondary cohomology of a space. And that's sort of what we did. We just thought about like how we can figure this out, and turned out it's not that hard. So the algorithm can be extended to general X. I think Bowers could have done this. He just didn't mention this because he only cares about a sphere, and I mostly also only care about the sphere. Okay, so this great way computes all D2 differentials, but not all differentials are D2s. So the next thing that we computed with the computer is what I would like to call E3 page products. Compute all E3 page products. So, I mean, the E3 page does inherit a product from the E2 page, but what I call E3 page product is something stronger. There's something that sort of captures sort of products, but sort of up to one filtration higher. So it captures some extra information. So for example, the relation that mu cubed is not eta squared sigma, but it's eta squared sigma plus eta epsilon. So there's a relation between elements in filtration 4, sorry, filtrations 3 and 4. And this so-called E3 page product will be able to capture this information. Like the computer will just tell you this relation right away. So this is a very useful thing to do. And another thing it computes is just all hidden extensions. That jump by one filtration. So the idea is that these hidden extensions actually help you compute lots of differentials. I'll just draw a very schematic picture about this. So let's say we have a class A and H1 of A. And it supports a D2 to a class I call B. And there's a hidden eta extension like this to C. So the claim is that we have a D3 on H1A, which is given by sort of eta times D2 of A. And this is given by basically C. So from this, we learned that there is a D3 like this. And a very useful feature is that the input data is everything that comes from this computer data about the E3 page. Like we have a D2, which is what the algorithm gives you this hidden extension that jumps at one filtration, which is also given by the computer. And now we know about the D3, and that's longer than 2. So this is very useful for like computing extra differentials. And using this, we managed to resolve all unknown D2s, D3s, D4s, and D5s up to the 95th stem. So there's nothing about the lengths 2 to 5. I mean, obviously 2, it just comes from the computer. The 3 to 5 is just that I looked at a list of unknown differentials in more stable stems, tried to solve as many as I could, and I just did a bunch of them. It turns out I happened to solve all D3s up to D5s as well. So I should say most of these arguments are quite easy once you have this framework about hidden extensions and extending differentials this way. Most of them just follow straight away. And so, yeah, so you can compute differentials that are longer than D2s using this data. And I think this is sort of the biggest improvement over what Bowers was able to do. So this has a formal name. So this, if you are familiar with syntactic spectra, these are products in mod C tau squared. So these are the computational results about like how this thing works. There's also the theoretical part that underpins these calculations, why these computer calculations does tell you something about any spectral sequence. So I'll just phrase this as a theorem. So this theorem will use syntactic spectra, but if you're not familiar with syntactic spectra, I'll not really talk about it for most of the talk, so that will be fine. So the theoretical theorem is that there is a co-continuous functor from mod c tau squared to modules over B op that is fully faithful on modules on the stable subcategory generated by things of the form c tau squared tensor nu x, where x is finite type. So this finite type condition is sort of necessary because the left-hand side is about homology, whereas the right-hand side is based on co-homology, and co-homology in general only works well if you are finite type. Give me a second, my computer's a bit messed up, it needs charging.
Could you just remind me what co-continuous means here? Is it means co-limits go to?
Sorry,
can
you say that again?
Co-continuous mean that co-limits go to co-limits, which are homotopy limits in the opposite?
Yes. Well,
and do you need to assume that x is bounded below?
Finite type implies bounded below.
Oh, I see.
Yep. So there's something extra you need here, which is that you need to say something about things of the form c tau tensor nu x, which is what you need for the D2 differential. And it's not of the form c tau squared tensor nu x, but there's some compatibility condition that I did not state in the theorem. So this is not the full theorem, like there are other properties of this functor that I don't fully list. Okay. So this is the theoretical result that underpins why these calculations work. And the point is that once we know what B is, it's a differential graded algebra, and we can do homological algebra on the right-hand side to do the calculations that we want. So one question that people like to ask when they see this kind of result is that, can we do it for longer differentials? Can we get everything about D3s and D4s and so on? And I just want to present some source of difficulty for doing this. So obviously you need to compute the tertiary steam-out algebra if you want to do D3s, and that is a hard problem. But also, what is it? The claim is in general it will no longer be a differential graded algebra. So instead it's an algebra with something that's a bit bigger. So there's a theorem so this is a bit funny to state, but I'll define this object. Less than n. This is the quotient of the sphere by killing elements in pi star S whose image in the Adam spectral sequence has T at least n. So you need to do a bit of work to formally construct this as an E-infinity ring, but then the claim is the n-Aristotelian algebra, which we define in the same way. The n-Aristotelian algebra is an E1 ring over this funny truncation. So I'll just go through a few examples. So we can draw the additive spectral sequence. Okay, so when n is 1, so this is a normal stimulate algebra. P equals 1 is this line. Everything above this line is killed. So we're left with HFP. So the ordinary stimulate algebra is an E1 ring over HFP. That's what we know. So when n is 2, we get an extra term. We get P squared as well. So the secondary stimulate algebra is an E1 ring over Z mod P squared. Now, if we go to n equals 3, then we are a bit sad. So we have Z mod 8, that's expected, but we also get eta. And now eta is in the picture, it's no longer pure homological algebra. We have to somehow deal with this eta that's hanging around. And we just need somebody to deal with that if we want to work with higher n. So that's sort of a problem to solve. Once we solve this problem, we need to compute the tertiary stimulate algebra. And then after that, we can probably do the same computations. Hopefully it'll not be too much slower, but that's sort of what you have to do to work with higher n. Okay, so that's that. Okay, any questions so far? Okay.
I wanted to make one comment about. Sorry. Can you go back to that nu cubed plus eta squared sigma?
Yeah.
So you were kind of, so you can see it right there, like there's that example and there's the example of hidden extensions. I just kind of wanted to point out that first example really is sort of a hidden extension if you think about it the right way. You start with, h2 cubed plus h1 squared h3 equals 0, right? Something equals 0, but then it turns out in X, but then it turns out to not equal 0 in atoms. So, I mean, it's some sort of like, compound or matrix. I think matrix hidden extension is maybe the kind of the right language for it.
Yeah, but I think I would like to call those as like E3 page products or mod theta squared products. And
right
here I'm just giving examples, but the second example is like the very classical notion of a hidden extension. But yes, these should be sort of, I mean, I am grouping these into the same category, which I choose to call E3 page products, and you might choose to call hidden extensions. Okay. Right. So I think a very useful thing to do is to say what actually is the secondary stimulate algebra, like as a DGA. It turns out it's like huge and a bit of a mess, so I'll not tell you what the full secondary stimulate algebra is. But there's one thing that can be done in a fairly reasonable manner is the secondary B0 or the secondary A0. So let's go to that. So this should be seen as a taster for what the full secondary stimulate algebra is like. So we can define sort of B0 in exactly the same way. So we take the sum over all k. Truncate to 0, 1. Suspension k of n of fp. But instead of taking endomorphisms over spectra, we take it over the integers. And this can be computed super explicitly. So we can start with representation of fp as a chain complex, z mapping to z in p over here. And because we'll be working with these a lot, I like to give these names. So let's call this x0. Let's call this x1. Then end of fp, this fp tensor fp dual. So this given by, there are 3 terms now. In degree 1, we have x1 tensor x0 dual. In degree 0, we have x0 tensor x0 dual and x1 tensor x1 dual. And finally, in degree -1, we have x0 tensor x1 dual. And these differentials, you can check that p minus p and p comma p. Right, so now we can try to just work out all of these definitions. And let's just start with, well, the first, this is k equals -1. We're looking at this, but this map over here has no kernel. So k equals -1 is just trivial. K equals 0, we're trying to grab this part. So when k is equal to 0, the kernel of the bottom map is x0 tensor x0 dual minus x1 tensor x1 dual. So let's give that a name. That's the identity. That's identity matrix after you have the right signs. So the names will go to the right. 1 is x0 tensor x0 dual minus x1 tensor x1 dual. And upstairs you have the null homotopy of P, which is mu, which I'll call mu naught. This is x1 tensor x0 dual. And I like to distinguish between things sort of like the in co-modular degree 0 and 1. So this in degree 1. Okay, so here in the bottom we have z adjoin 1. And this z adjoin mu naught. And the map is P. Okay, so this k equals 0. Let's say k equals 1. We're looking at this section. So we're basically taking this and quotient out by the image of x1 tensor x0 dual. So let's again look at the bottom part. We have x0 tensor x1 dual. That's the Bochstein, that's beta. So here we have beta. And upstairs we have we have x1 tensor x1 star, which we can check is mu naught times beta. If mu naught times beta, x0 dual and x0 contract to 1. So we have z join mu naught beta. And we also have x0 tensor x0 dual minus x1 tensor x1 dual on top. So I'll call that tau. So tau is, so it sort of looks like 1. But it's in degree 1. And it p times this is trivial, so this plus fp join tau, and this p comma 0. And finally, there's the k equals minus 2. So k equals 2, you get this modeled by p. This you can check should be equal to, well, the only thing that's left is tau beta. I mean, it is tau beta. So it's like beta, but upstairs. Okay, so this is the secondary A0, and I'll just summarize this by saying that B0, oops. So below you have something that looks like A0, but it's now over B, sorry, now over Z, and upstairs you have the null homotopy of P, and then an extra copy, which we sort of expect because we know what the homotopy groups look like. The map is like P comma 0. So if you stare at this as a chain complex, it's just sort of A0 on top and A0 below, because sort of you can just quotient out the left-hand side. You just take the quotient on the left. That map is injective. But we're thinking of this as a DGA and not as a group. So there's the product structure. Most things are already written here, but we have the last relation, which is we have to figure out what beta mu naught is. So beta mu naught, we contract x1 dual with x1, so we get x0 tensor x0 dual. And this equal to tau, which is the thing that looks like 1, but in degree 1, plus mu naught beta. So there's a non-trivial relation upstairs that sort of like crosses over between the z bit and the, well, the mu naught bit and the tau bit. So this is a rather important relationship. It means that we can't just kill off the left-hand side. What we can do is that we can kill, because p times tau is 0, we can kill off p times the left-hand side, and we get something that looks like fp join mu naught beta plus p tau beta and the z mod p squared with 1 comma beta. So there's a secondary A0, and we can compute it fairly explicitly. And the key relation is this one that we wrote over there, beta mu naught, oops, beta mu naught is equal to mu naught beta plus tau. And we should think of this as somehow encoding the fact that beta is the thing that detects P. So if you look at the cohomology of A0, there's this element H0, which is sort of comes from beta, and it just sort of is around it, is a term, and a priori there's nothing that connects it to like multiplication by P. And here mu naught is a null homotopy of P, and this relation just somehow ties the two together. Okay, so this P0, and now we can compute sort of the secondary cohomology of various things. So I guess the simplest thing to compute is what we would call, I'd like to call this blackboard bold K. So this cohomology of the sphere, in this case, is the integers. And I'll not go through the whole calculation again. It's a fairly straightforward manipulation, but this is B, and your quotient out beta on the right. So this is FP join mu naught plus FP join tau FP to Z mod P squared. And then beta mu naught is tau. So this is the starting building block of everything. It's the cohomology of the sphere.
So is this B naught mod beta B naught, or is it also B mod
there's
beta,
a zero.
B?
Yep, sorry. So obviously for the full secondary student algebra, so for the full secondary student algebra, this is still the correct description of the secondary cohomology of the sphere. It just naturally extends to algebra over the full, by which I mean this explicit chain complex is the correct cohomology of a sphere in the full case as well. Okay, so let's try to look at something more complex, something with two cells. So the first thing we might look at, I'll just draw a small table. So it's Z mod P. So the cohomology of X, sort of by definition, it is just B0 itself. That's sort of the definition. But we can try to write it in terms of like K. So we sort of have two, as a group, or as a chain complex, it's K in degree 0 plus K in degree 1. So, but then there's a relationship where beta of A is B. So this sort of just recovers the description of B0 itself. And this can be distinguished from like two copies of Z by looking at the action. So here, two copies of Z as a chain complex still looks exactly the same, but beta of A is now 0. It's just literally two disjoint copies as B modules. So these two can be distinguished using just ordinary cohomology because we have a cohomology operation beta that just carries A to B. But the more interesting bit is Z mod P squared. So as a group, you'll find it's exactly the same. But over here, the relation as a beta times A is equal to P times B. So if we just take homotopy groups, then P is 0. So it looks exactly like the second case. So the ordinary cohomology is the same as two copies of the sphere, but there's something extra interesting hidden here, which is there is a non-trivial secondary cohomology operation. So we can look at the cohomology operation associated with the fact that beta is 0. So this will be given by, I'll draw an arrow. We can compute beta A. So beta times beta is just literally 0 in B0. There's like nothing in degree. There's nothing else. So null homotopy of beta times beta can just be chosen to be 0 itself. So there's 0 times A plus beta times the null homotopy of beta A. So beta A is P times B. So its null homotopy is mu naught B. And we've seen that beta mu naught is equal to tau plus mu naught beta, and beta times b is 0. So this just equal to tau b itself. So what we see here is that there's a secondary secondary cohomology operation carrying A to B. So this is something we can do very explicitly, and so it sort of distinguishes between these two cases, both of in a more homotopy invariant manner, which there is a secondary cohomology operation. And in general, you would see that like the action of the secondary cohomology of the secondary standard algebra on secondary cohomology groups just encodes all secondary cohomology operations acting on cohomology. Okay. Any questions about this?
So
okay.
Is it
So,
tau b or b?
Right. So I mean, tau. So it just has to be in the upper. It has to be in like cohomological degree 1 just for like normal homological reasons. But then, I mean, they're sort of the same thing because it's just on homotopy groups there are just two. I mean, this is an element in the homotopy groups, and like in both cohomological degrees, they're like Z mod P. So yeah. I guess if you think about the normal cohomology, yeah, they're the same thing, basically, in this context. In this context, it's the same thing. Like in general, tau B and B are very different things, but here we're abusing tau to mean something slightly different. Okay. So I guess that's a good point to start getting into the main topic. So this what secondary cohomology is. It captures information like how do we compute D2 differentials? I'll get a new page. So how to compute D2s. So let's start with a very naive guess. So the E2 page is given by X over the C0 algebra. So a good guess is the E3 page is given by X over the secondary C0 algebra. And this is sort of true. It's not exactly true, but I'll tell you like it's sort of. So at the end, the answer will be they're not equal, but the right-hand side is what you should be looking at and not the E3 page. So let's just think about how to compute X over the secondary C0 algebra. So one answer is that a computer can just calculate it. It's a DGA, it's homological algebra. Computers can do homological algebra. So one answer is by the computer. And the other answer will be to compute D2s, basically. So I guess I should put in the actual argument. So X B, I'll take it from a secondary cohomology of X to blackboard bold K. And just recall that blackboard bold K is now that the secondary cohomology of the sphere. So the idea is to use Pozdnikov filtration on K, since the homotopy groups of K are FP adjoint tau mod tau squared. So if you have the Pozdnikov filtration, we get okay, this sort of not quite in the right place. Let's see. Okay. So this FP adjoint tau mod tau squared converging to that. So there's like a very standard spectral sequence you might want to use if you are just trying to compute things by hand. And we can look a bit more into the left-hand side. So FP, this is a secondary steam-rod module, but it's induced by like a normal steam-rod module. So by base change, this is equal to X over A tensor over B, secondary cohomology of X, FP. And then this tensoring, it just gives you X over A of cohomology of X mapping into FP. I guess I'll just put this guy over here as well. So we have the spectral sequence whose E2 page or E1 page, whatever you want to call it, looks like this. So downstairs we have one copy of X over A, and upstairs we have another copy of X over A. And there's a bunch of differentials between them. If you think about it, the Postnikov tower of K is really just a cofiber sequence because there are only two non-trivial homotopy groups next to each other. So this really is just a cofiber sequence. And so there's only one set of differentials, which goes from X over A to X over A. And if you keep track of the right degrees, you'll find that they are in the right degrees to be the D2 differentials. So this is the theorem. These differentials are the Adams D2 differentials. So the point is that these differentials can be computed by a computer. It comes from like just the cofiber like the cofiber sequence from the Postnikov tower of like blackboard board K, and you can like apply the snake lemma. You just trace around and you compute these differentials very explicitly if you have like a cofibernate replacement for the secondary cohomology. So these differentials can be computed by a computer, and the theorem is that these in fact are equal to S D2 differentials. So there's how the computer manages to compute these D2 differentials. So we can go back to the original question of like, okay, so what is the E3 page? And it's not exactly X over B, right? If you think about how to compute the E3 page, you have these D2 differentials, you take the kernel and then quotient out by the image. And here on the bottom layer, you take the kernel only. On the top layer, you take the quotient only. So you're sort of like remembering a bit more information in X over secondary steam-not algebra. So note, X over B is not E3. And my claim is that it is better. And it's not better because we separate out the quotient and kernel steps. I mean, that's a bit useful, but that's not the whole point of this. The whole point is that when you sort of glue these together to get X over B, you actually get, you have to solve extension problems. And those extension problems, which can be solved by a computer, contain the important information we're looking for. So the extension problems encode what I call the E3 page products. So I'll work this out explicitly in the case of the hidden extensions. So for example, if let's say A and B are in X over A, then D2 of A is 0, D2 of B is 0, A times B is 0. So the product 0 on the E2 page, we can ask if there's like a hidden extension on the E3 page. So pick lifts, I'll call square brackets A, square brackets B in X over B of A and B. If we look at the product in X over B, then it cannot have anything from the bottom layer because it's just trivial on the E2 page. So it must be something from above. So this will be of the form tau times C for some C in X over A. So this tells us there is a hidden A extension from B to C. So this is how this, so like looking at x over b instead of just the Adams differential gives you much richer structure about these hidden extensions. And similarly, if a Massey product vanishes on the E2 page and the product actually vanishes in the E3 page, then you can similarly say something about the Massey products, and all of these can be computed by a computer. Okay. So these are most of what I want to say about like the theory of how these things work. So I guess, are there any questions about this?
So the C is now defined in the co-kernel of D2?
The C is defined in the co-kernel of the D2 differential, yes. So these classes are free to not be permanent. So here's an example where they're actually not permanent. So, I mean, there's a fake example, but it's also an example. So let's say you have something like this. So there's H1, there's eta, and there's a D2 differential here. Then what we should learn is that we should be able to divide this differential along eta to get a D3 like this. And this indeed true. You can like prove that this works. And yeah, so from this point of view, it's actually very important to be very flexible. We want to be, we should be able to work with things that are in the co-kernel, but it doesn't have to survive. And similarly, on the other way around, if you work with things that are hit by differentials, like in the original example, if we just work in a very classical sense of a hidden extension on the E-infinity page, then everything is 0. So it doesn't make a lot of sense to say that there's a hidden eta extension from here to there when both are just 0 in the homotopy groups. So in that case, it's important we don't just like ignore or just kill off everything hit by differential right away. We want it to sort of remain a bit in this world. And the correct way to keep track of all of these things is to use syntactic spectra, which if you don't know about, it's a great thing to learn about. If you do, then hopefully these should make a lot of sense already. Okay, so this is the theory. I guess since we're here talking about machine computations, I'll just say something about the algorithm. So the work you have to do is that you need to find so how to actually do computations. So the important thing is to find cofibrant replacement of, oops, the secondary cohomology of X. And there's a trick here, which is that we start with a, well, free resolution of the ordinary cohomology, free resolution. The second step is that we lift this to over A. So we lift this to a chain complex over B. So we have like chain complex over B. And so basically we just put in the same, I mean, if P0 bar was free on 3 generators, you just make P0 to be free over B on the same generators. And then, so the chain complex in the sense that successive compositions are homotopic to 0. So 3, I'll have to give this name. So this will say D0, D1, D2, D3, D4. 3 with the pick null homotopies. Of dk plus 1. And we can't just pick them arbitrarily. So this is the step that requires actual work, which is what the computer does. We want the threefold Massey products to be trivial. And so this, if you write down what exactly this means, you have some recursive relation to solve for, which you can do with the computer. And then after you've done this, so let's define. So we compute. So once we have these null homotopies, we can assemble these into a total chain complex. So compute total chain complex. Well, I guess the total chain complex because each of these terms is a chain complex, so you just like put them next to each other, and then you have maps, and these homotopies will also show up. Total chain complex is a cofibrant replacement of some module M such that pi star M is the cohomology of X adjoint tau mod tau squared. So notice so far we still don't know what the secondary cohomology of X is. But then if we do this procedure, we end up with a chain complex that is a cofibrant replacement of a module that looks like it could be the secondary cohomology of X. And so basically with this, we're almost done. We just have to make sure this actually is the secondary cohomology of X. By obstruction theory, the space, the set of such M is X 2, 1 over A of cohomology of X, cohomology of X. So if this group is trivial, which is the case for the sphere or like sphere mod 2 or TMF KO and stuff like that, then this thing must be a replacement of the correct secondary cohomology group. If not, then we have to be careful. We need to there might be two options, in which case we have to run the algorithm, compute some differentials, and then check if we got the right one. If it's not, then we have to pick different homotopies in step 3, and it will result in something different. So that's a bit of work to work out. My algorithm only works in the case where there's only one choice, as in like this set is trivial. So I just pick null homotopies randomly, and then whatever ends up will be correct, which is usually trivial. And once you have the cofibrant replacement, lots of things can be computed using like ordinary homological algebra. There's a bit of work involved in making things work, but it's mostly busy work rather than like actual mathematics. So I should say that this algorithm that ends up showing up here is exactly the same as what Bowers did, but to phrase it in a different language. Okay. Any questions so far?
You say that in point 3, you say the bracket should be equal to 0. Is it enough that it contains 0?
Right. So you have to pick null homotopies so that with these choices of null homotopies, the bracket is literally 0.
Oh, of course. I see. Sorry.
Yeah.
Thanks.
And okay, so if you just pick, if you start with something that's not a cohomology of a spectrum, and then you try to do this, it's not always possible. So basically, it's not possible in the first step, and then like, the first time it might be possible, everything afterwards could be possible, and so you get some obstruction to this lifting, and that corresponds to the obstruction in the obstruction theory. So here I'm working in the case where there's no obstruction because we know there is a lift with namely a secondary cohomology, but sometimes if you just start with an arbitrary steenoid module, it need not lift to a module over B. So for example, if you have the module that's like the cofiber of H4, because H4 supports a D2, there's actually no B module that lifts that. So there's an obstruction theory, and I presented half of the obstruction theory here. Anything else? guess there are 2 minutes left, so maybe I'll just show you where the code is and show how it's run. So the code's on GitHub. It's here, and CI is not passing, but that's actually the compiler's fault and not our fault. The compiler has a bug. So there's the code, and here you can compile it. I've compiled it already, which takes a while. So you can begin by trying to resolve your module. So here it asks what you want to resolve. I want to resolve S2. The save directory is very important because each of the steps requires like recomputing the differential, and if you just save recomputing the resolution. I mean, each step requires a resolution, and just having it saved is nice. So I'll just pick a random name, save. How far do I want to compute the 64th stem, and s equals 32. That should be pretty good. So it'll take a while to compute. A few seconds, should be done soon. There we go. Oh, okay, that's a bit ugly. Let me do that again. So there are shorthands. Right, so this time it's instant because it was saved, and it prints an ASCII description of like an ASCII picture of the X group. So this just, just tells you it did something. This mostly for the next step. So this just compute normal X. So now we want to compute the D2s. So I'll input the same set of data. Now it's computing the D2, so it'll take a while, not too long. So this is all up to the 64th stem. Yep, so now it output all the D2s. So you can just find something random. Let's say D2 52,5, that's 1. That's a nice differential to have. You just output all the D2s. And we can compute products as well. So again, S2, we have a save file, 64, 32, and I would ask what the product it is. So we're going to compute H0, N is 0, S is 1, the class is 1. Now it's computing products, and it'll output the product as well. This computes all the secondary products with H0. So for the data set up to like t equals 140, it took around maybe 5 days to compute. So to compute D2 differentials, it took, I think, 3.3 hours on 40 cores. So it's quite parallelizable. It takes 40 cores to get up to t equals 140. It takes 3.3 hours to get to the 140th stem. But then each product also takes like a long time. So H0 product takes around 2.5 times as long. Now it's done. So we have H0 products. Yeah.
So does that include the sort of complicated H0 extension in the 45 stem? So so there's this class H0, H3, sorry, H0, H4
let's see, 45
cubed, which has this, which Dan can.
Which one is it?
So let's see. So from in the 45 stem, from filtration 4 to filtration 6, we sometimes draw a hidden 2 extension.
Filtration 4, to filtration 6. Okay, so we have to think about what exactly that means.
Yeah, that's the point. That's the tricky thing, right? Is that it's sort of, if you want to be formal and precise about it, what it really is, it's a hidden 4 extension on
right.
H4
hidden 4 extension, we can do that. So, right. So we start with this, 45,3, right? 45,3 times H0 is this plus tau times 1,0. So this times H2 is this plus a bit of this. And H0 45,4 is just 0. So we get 1,0 times H0, so we get this. So we do get that relation.
Could you repeat the conclusion again? I didn't catch the argument.
Right, so we have I'll just call that 2 tilde because that's sort of the better name. So 2 tilde of H3, H5. So H3 squared H5 is, we can check, 1. So it's this. So it's this particular lift of H0, H3 squared H5 plus tau times H5 D0. So that's what it told us. And here, in the next line, it tells us that 2 tilde times H0, H3 squared H5 is 0. So we get 2 tilde squared times H3 squared H5, just iterating this, is tau times H0, H5 D0. So the point is that for every element of survives D2, we need to pick a fixed lift to like X over the secondary student algebra. So here there's a particular lift. For this particular lift, 2 tilde times this is this plus that. And then for that particular lift of H0, H3 squared H5, 2 tilde times it is 0.
Yeah, it's those words choosing a particular lift. That's kind of the key point here. Yeah.
Right. So you don't have, so the lift itself doesn't matter, but what's important is that the lift is consistent throughout the whole data set. So it's important that here on these 2 lines, like this lift is the same as this lift. That's why we can do a computation. Right, and this kind of relation is actually very tricky. It's tricky, but also super useful. So for example, over there's a differential over here. Oh, this is a horrendous mess. But see the D2 from here to here. And I think one differential that was left unresolved in more stable stems was the differential from H0 to 7H6 to here.
I don't know what here means.
I don't think we see
anything on the screen that corresponds to the word here.
Yeah, I don't think we're seeing your
pointer. Oh, okay. Let's see. Okay, so how do I do this? Right. So there is. So this we have H6, which is at the bottom of the 63rd stem.
Yeah,
so there's a bunch of D2s. 63,1. So there's H6, and there's this much of D2s that are standard. And obviously the computer does give them, but also everyone knows them, sort of. And then it goes all the way up to H0 to the 6th, H6. And then the next one after that, we have a D3, which we also expect. Okay, I think I should not do it like this. How do I do this? Does this work? No. Okay. Maybe we should look at something less messy that's easier to see. Right, okay, let's look at this H5, right? So we have D2 H5 is H0 H4 squared. And so we can compute the D2 on H0 H5 and H0 squared H5. So if we want to apply the previous argument, we want to say there's a hidden extension from H0 cubed H4 squared to the thing the D3 hits. But that's sort of not super well defined because there's an extension over there. But sort of this more refined notion of a hidden extension that we talked about previously just automatically gives us this D3 on H0 cubed H5, which is basically the fact that like H0 to the 4th times H4 squared is H0 delta H2 squared.
This should apply in the 15th stem as well, right?
15th stem? No, it doesn't, because, okay, so it depends on, so you can use the exact same argument. The point is that I guess we have to know that the D2 differential on H4 actually hits twice of sigma squared and not like twice of sigma squared plus kappa. And the point is over here on the right, we know the differential on H0 squared H5 hits something that is 2 divisible because it's like H0 times the differential on like H0 H5. So here we don't have that trick unless we just say, oh, we know this differential because 2 sigma squared has to be killed by something. If we use that argument for the differential in H4, then we actually know that H4 kills 2 tilde sigma squared, and then we can apply that argument. So I mean, you could do that. Another way to get a D3 on H0, H4 is that there's actually a hidden G extension, a hidden kappa bar extension from H0, H4 to M in degree 35,7. And there's also just a normal G extension from here from D0 to E0 squared. So you can divide along the kappa bar extension from H0, H4 to M to get the D3 differential. So that's one way to get a differential. I mean, it's a very bizarre way to get this differential. There are like way better ways to compute this differential, but it works.
Well, but that's sort of like the wrong framework. What you want is as many different proofs of as many facts as you can get your hands on.
I agree.
Because when you get to the 140 stem, like you're going to need all the help you can get.
Yes, I agree. And this can also, in theory, be automated by a computer. It seems like a huge, it's like annoying to do, but there's nothing that prevents us from doing it from a theoretical point of view. So if there's a Leibniz rule that just goes between all these different degrees, it would be very nice to see how far it can go. So I think it has trouble. So this technique gets you all the way up to the 35th stem. It would have trouble with this H3, H5 class. So this requires sort of a hidden extension that jumps by 2 filtrations. We need to show that there's a hidden sigma extension from H4 squared to X. So that's what we need for this D3, a D4 on H3, H5. So that's the first step where it's not obvious how this technique can help you compute the differentials.
So that's really interesting. You're putting your finger sort of exactly on the place where kind of like, you know, the cofiber of tau squared sort of breaks down. That's interesting.
Yep. Well, we don't know, right? Because it could be that if we go up to the 140th stem and use all back and forth product, we could somehow get up to there. But I think like in your previous talk about like whether we can get D2 on D1 using the Leibniz rule, like we can't get it yet, but in theory, if we keep going, we might be able to get it. I also didn't try very hard on this H3, H5, but at least the obvious ways don't quite work. Oh, there's also something funny. It's not obvious from this that G is permanent. It follows from like Adams periodicity, but I don't see a way using just these products to see that G is permanent.
Yeah,
unless I'm missing something obvious.
Yeah, see, some of these things you have, there are sort of alternative computer-based arguments. Like, for example, for G, why can't G hit P squared H2? Well, if you look at the motivic weights, or equivalently, you look in the Adams-Novikovs, the filtrations just aren't compatible.
Yep.
And then similarly, the H3, H5, we actually do have a computer-based proof for H3, H5. Because that one's detected by, you know, the algebraic Novikov spectral sequence from this motivic perspective. So what you really want to do is take these different computer programs and you want them to communicate with each other and feed each other their output and see what they can then, you know, propagate from there.
Yep, I agree.
It's a lot of work. It's a lot of person hours in the coding, all of this thing. But, you know, we got a couple decades, so, you know, we'll get it done.
I think one thing that will be very interesting is to see if this can be done with like proof assistance. So because they sort of help, like you might have to manually write an argument, but at least it could help you like just, I guess, formally prove lots of these like fiddly arguments about all sorts of motivic and Adam stuff. Hopefully we'll catch some errors, and there are some automated techniques to come up with arguments sometimes. But so that's a story for another day.
Yeah, we seem to have sort of drifted into the question period seamlessly, which is fine, but maybe we should stop for a second and make sure we thank Dexter for his talk. So let's do that. Other questions or comments?
Yes.
Do we know the secondary cohomology of RP infinity or CP infinity or KU or anything like that?
KU, there is a, yeah, for KU, there's a unique lift, I think. But I think if you just compute X, then it's trivial. So for KU, for KO, for TMF, they're all trivial. For, I don't know about RP infinity or CP infinity. I think those are non-trivial. Basically, what you need to know is you need to know attaching maps up to like filtration 2. So what the cohomology tells us is attaching maps up to filtration 1, and you need to somehow figure those out. I think it's, some of it is probably known, but I don't know.
So you ought to be able to, automate the D2 in the atom spectral sequence for TMF.
It can be done. I did not write the code to make that happen.
Right. That ought to be possible. Yeah.
Actually, I can probably just, it's not a lot of work, but we also know all the D2s. So I wasn't particularly motivated to figure that out.
Yeah, no, it's reproducing previously known stuff, but still, like, just, it's just assembling all these different, computer machine computations. That's just something that's kind of like sitting there that could be carried out. What about the C-motivic secondary steam-rate algebra?
I have zero idea. So an embarrassing thing is I still have no idea how Bauer's computed secondary steam-rate algebra. I'm not sure if anyone does. He has this very long book, which I think.
Actually, he uses this secondary Hopf algebra structure of the second. I really like your construction. Can you actually see the co-product also in an elegant way?
I think it's easy to see that there is a co-product, but I think it's not. Is it easy to see that there's a co-product? I think it's not too hard to see there's a I think I thought about this. I didn't see an obvious way, but also it doesn't seem like it should be that hard.
I actually tried to read my own paper on this, and then I was surprised how technical all of this stuff was about this diagonal. So I was just wondering if you have a cleaner way to do this.
Okay, yeah. So right. I remember what I figured out because I don't actually know an obvious way to write down the co-product in a normal steam-rate algebra. That's like not super obvious. Like the easiest way is that you compute like the dual steam-rate algebra that has a natural product and co-product, and the normal steam-rate algebra is a dual of that. I think if you just look at like end of FP and try to write down a co-product on the homotopy groups, I think if you fiddle around a bit, you can, but it's not super. It's not like a very clean construction. Yeah, so there's like.
I guess that's somehow what Adams has these notes from around 1970, where he does this for generalized homology theory, where he has a fair amount of maneuvering, which I think is my. He has these lectures on cohomology theories. These that are typewritten, not the blue book, but some earlier notes. This is Springer lecture note, where we're just thinking about this sort of discussion of how to get at the Hopf algebra structure from a homotopical point of view. But you probably know this already. I wanted to ask, this description you gave of how to get a cofibrant replacement over the secondary steam-rate algebra looks quite similar to this sort of rough sketch I've understood of how Gush and Wang's program works in order to get resolutions for the algebraic Adams-Novikov spectral sequence to produce. Is that right, Daniel? Is there? It sort of starts with a. Is this a basic idea of starting with a resolution and then sort of lifting it and trying to make it into a resolution again? Is this?
I don't have I personally don't have like a clear answer to that. I'd have to like sit down and like really tear it apart and see what's going on again. I don't remember. Yeah. If I ever knew in the first place, which I'm not sure that I did.
I think the answer is yes, but it's just because there aren't that many ways to compute. Okay, so there are two reasons why it's done this way. One is that there aren't that many ways to compute cofibrant replacements. The other is that you want a way to compare it with like your usual X. So there's like the normal X, which comes from the, like you have a fixed minimal resolution, and then you want to know like, basically you need a way to relate your like cofibrant replacement over the secondary steam algebra with your normal free resolution, and you want to compare the terms, and lifting it this way is a very easy way to make sure you just get a direct correspondence between the terms.
Any other questions?
I wanted to ask, so in your paper on the archive, what's the title? The Adams differentials via secondary Steenrod algebra. You remark that the definition of a shift algebra in these pair modules is really similar to the like Goers-Hopkins work of Piotr and Paul van Koffenit. I was wondering if this is like superficial or whether there is like a real theoretical interest and whether or not you think like higher truncations and other things could be related to like future pages of the Adams spectral sequence.
Right, so I'll go back to here. So they're basically all contained in this theorem, which is that there's a correspondence between like mod c tau to n, which is the Piotr's abstract Goers-Hopkins version of the story, and modules of the secondary Steenrod algebra. So, I mean, they sort of just directly correspond, and this version works for like the n-ary Steenrod algebra and mod c tau to the n as well. So there is a direct correspondence between these two, which is, I mean, the proof is exactly the same. The proof uses nothing about 2. So they just stated it for 2 because that's what we're working with. So yes, I think the answer is that they are basically very related. So what I'm working on is sort of a replacement for that paper that just works in this framework. And basically what I do is I just work fully in the framework of the synthetic story and not talk about, I mean, the concepts are the same. It's like the shift algebra is indeed a special case. And I think in that paper, I said there is similar and not a special case because technically in Piotr's work, he needs a lift up to all n, which doesn't quite exist on the secondary base, but it's like literally the same definition.
Another question? Okay, then we'll wrap it up here for today.